Hi, I'm Matt Holliday and welcome back to my class on Programming in Go. So in this section what I want to do is drill down into slices in more detail. And I've promised that for a while now. It's a little bit technical, but I think it's worthwhile because it'll help us understand slices a bit better. And so there's a couple pieces here. I want to talk about the difference between a nil slice and an empty slice. And then I want to illustrate some things about the difference between capacity and the length of the slice. So we're going to start in the playground. In fact, we're going to do most of this in the playground. And what I have in front of me is a little program with a complicated printf. Okay, I'm going to print out the length of a slice, the capacity of the slice, the type, whether the slice is nil or not, and then finally I want it to give me its debugging view of what the slice looks like. In other words, the #v view of the variable. And of course, S here is a nil slice, so we're going to start with that one. And when I run this on a nil slice, the length is 0, capacity is 0, fine. The type is slice event. That actually is the one thing that's not going to change. And it's true that S is nil, okay? Because I didn't do anything. I just declared S as a variable of type slice event. Okay. Now, what's interesting is how it prints out, because it prints out this brackets and int, and then in parentheses it puts nil, okay, which is a little different from the type that showed up in the third column, which was just the brackets and int. So it's doing a little bit of work here to actually say, hey, by the way, this is actually a nil slice. Okay, so let's start. We're going to create some more of these slice variables, and the next one we're going to create, we'll call it T, and it's going to be a slice event, but it's going to be an empty slice event. And we show that by having these empty brackets. So we didn't put any values in there. And I need to change these little things right here. If I'd been a little more clever, I probably could have just had one S and a whole bunch of these little bracket numbers to use the same variable over and over. All right, but let's run this, and we're going to get a different answer, okay? The length and capacity are 0. The type is the same, and the type, again, is the one thing that won't change. But now, S is not nil. I mean, T is not nil. So we get false for the is nil case. And then we get this brackets in with braces that are empty, and that looks like what we typed in the code. Okay? So the first one is nil, and the second one is empty. I want to do a couple more cases, though. All right? So I want to create a U, and we're going to make it. And we're going to make it as a slice event with length 5. Okay, and then we'll ask the length and so on. All right, and then I'm going to do one more, and that's going to be V. And I'm going to change something, and you may not have seen me do this yet. I'm going to put two numbers here. Pardon me. So the first number is the length, and I'm going to set the length to 0, and the second number is capacity. So if I only give it one number and make, the U gets made with size 5. It has length 5, capacity 5. V is going to get made with length 0 and capacity 5, which is slightly different. And so let's take a look right now and see what happens when we run those. I need to add my V case here. Okay, so we're going to add U and V down here at the bottom. Okay, so U comes out as length 5, capacity 5, fine. It's not nil, and it's an int with 5 zeros. So when we make a slice, and we just say make a slice of length 5, and we don't provide any actual values, then all of the values in the slice are set to their default value for the type. And since it's a slice events, they're all zeros. If it had been a slice of strings, it would have been a bunch of empty strings. But in the case of V, it's a little different, because I made it with length 0 but capacity 5. So it prints out the same way as T did as an empty slice, because it is empty. It has length of 0. It has no values in it, but it does have space for 5. Okay? And the reason we would do this in practice is I wouldn't do it for 5. If I knew I had a slice that was going to have 1,000 things in it, it's more efficient for me to go ahead and say, hey, make it with space for 1,000 things, and then I'll fill them in. Okay, now there's a trick to that. Okay, I'll show that in a second, but I just want to point out these are different. And what I want to do now is I want to jump into the slides real quick because I want to show what this looks like underneath. And what I have on the slides now is a picture. So the first picture is I'm showing what a slice descriptor looks like for some slice. So I'm just going to draw a line here. Okay, this slice wasn't in the little program we had, but presumably this would be something like A is defined as a slice of int with the values 0, 1, 2, and 3. Okay, and what we get is a slice descriptor that has length 4, capacity 4, and a pointer which points to the first element in the slice, which is just a pointer to a sequence in memory, right? Because we know the values in the slice are all going to get lined up in memory one after another, so it's enough to have a pointer to the first one. Fine. Now, how does that relate to the STUV variables that we just saw in the program? So S is a nil slice, right? Its slice descriptor just has zeros. So it has 0 length, 0 capacity, and a null pointer, which is very convenient because when we declared, var sint, and it wants to provide a default value for the slice variable, it just writes a bunch of zeros into memory, and we've got a slice variable that starts life as a nil slice. And that just works very nicely. So how about T? T is an empty slice. It has no capacity. So again, if I look at the slice descriptor, 0 length, 0 capacity, but it has a pointer to something. And what Go does under the hood is it has a pointer off to a special location in memory. And I'm not going to talk about what that means really, other than it's a non-null pointer, but it's sort of like a sentinel value. It's a special value that just marks this as being, okay, it's a slice, it's not nil, but it doesn't have any storage. That brings us to U. And U is just a regular slice. We made it, it has 5 zeros, so it has length 5, capacity 5, and it has a pointer to the actual storage. So that's just the same case as what was on top of the slide, right? It's a real, don't want to say it's a real slice, but it's a slice that has something in it. Okay? And where do we get to with V? Well, V is a slice that has 0 length, capacity 5, and it has a pointer. Now on the right-hand side of this, I drew a little box with 5 empty boxes in it. I don't know whether Go puts zeros in there or not. It doesn't matter because logically speaking, the slice has space for values, but it doesn't actually have any values. So what's in that box right now, it doesn't matter whether it's initialized to 0 or garbage. Okay? The slice is empty. It has no entries. It just has space for entries. So if we look at all of these, if we look at these 4 cases, STUV, okay, the actual slice descriptor in each case is slightly different. There's 3 things in there, length, capacity, and pointer, and one of those things is different, or more, is different in each one of these cases. Okay, so we have a nil slice, it's all zeros. We have an empty slice, it's got no length or capacity, but it points to a sentinel, so we know that it's empty and not nil. We have a slice that actually points at storage with values in it, and then we have a slice that points at some storage that has no values, but it has place for them. Okay, now, why do we care? And to answer that question, I'm going to go to one more slide. I think I'll just do this on a slide. Here's an example of where it matters whether it's nil or empty. Because when we go to represent the slice, say in JSON, there's really 2 cases. If you look at a JSON property that can be an array, well, any JSON property can also be null. And that's what's going to happen here. If I take the nil slice and encode it into JSON, it's going to come out as null because there's nothing there. If I take the empty slice and encode it as JSON, I'm going to get a pair of square brackets with nothing in them. In other words, an array or list of length 0. And so these things are actually practically different in terms of how they get represented to the outside world. And I can do the same thing with a map. If I change this ever so slightly and made a nil map and an empty map, I would get a JSON null, and I would get a pair of curly braces with nothing in them instead of square brackets, just because the map would show up as a JSON object with no properties. But I want to bring out one thing here, and that is a mistake I sometimes see is people will ask the question, is A equal to nil when they're asking about, some slice, is it full or not? And that's the wrong question, because there's two cases where a slice can be empty. It can be nil or it can be an empty slice. And so the right way to do this is actually to ask, is the length of A equal to 0? Okay? Because that's what we really want to know. Is the slice empty or not? And the length is 0 if it's nil, and the length of 0 is it's empty. And so this case covers both properly. In almost no case do we want to know whether it's nil or not. What we want to know is whether it's empty or not. And so we can just ask the length. And this works because asking the length of a nil slice makes perfect sense. If it's nil, it has no values, it's empty, its length is 0. It doesn't crash. We don't have to worry about checking first, is the slice nil before we ask about the length. But it's safe to ask the length of a nil slice. That's very convenient. And that lets us write it in one way correctly to cover all the cases. Okay, so I want to go back to this first slide, which summarizes what I just showed in the playground. But I want to bring out one thing. I had a thought, and it's something I want to mention, and it's specifically this case right here when I made V. Okay, and here's a common mistake that I make, and that is, if I've created V this way, it has space. And so what I want to do is I actually want to assign to it, I want to do something like, V0 gets some value. But every once in a while, what I'll do is I'll do it this way and say, hey, create capacity for something, and do append. All right, and that's fine because the slice is empty and I can append to it. So that works. Okay, and now I'm coming to my point, but it doesn't work here. If I create a slice of length 5, it starts out with 5 zeros, and I can start inserting things into those spaces using the subscript notation. But if I do an append, where does the next thing get appended? Well, it gets appended after the 5 zeros. This is the thing that actually gets me every once in a while. I'll create a slice and I'll forget to put 0, 5 or something. In other words, I want to save the space to put stuff in it, but I forget to give it two values to say the length is 0, but the capacity is non-zero. I'll give it 1. It'll have a length, it'll have a bunch of zeros, and then I'll start appending. But I'm not appending to a slice of length 0. In this case, I'm appending to a slice of length 5. And so I get my 5 zeros, and then I start getting values that I actually care about. Except when I do this, it's usually I've got 1,000 zeros, and then I've got values I care about. And it prints out kind of funny, and I'm wondering what's going on. So that's what I want to point out. This one thing that thought occurred to me is, yes, if you want to reserve space for a slice, make sure you put the 0 in there. Don't just make it a slice of length 5 unless you mean for it to have 5 elements to start with. If you want to reserve space, make it length 0 and give it capacity that's non-zero. And then you can append to it knowing it's a slice of length 0, and your first append will put something into the first spot. Which brings me to one more point. And I don't think I actually said this anywhere. It is perfectly okay to append to a nil slice. If I have a slice defined like this, var s is a slice event, it's nil, I can start appending to it. Because appending to an empty slice just means whatever I put into it, it's going to allocate some memory and copy in there. So again, appending to a nil slice is not the same as inserting into a nil map. You can append to a nil slice. It's perfectly okay and people do it. And then you'll end up with a slice that's not nil. And of course, like I said before, you'll do something like s is equal to append s something. And as soon as you do that, s will get storage, and you'll assign a slice descriptor back into s that properly references that storage. Okay, so now I want to move into the other section. Right? I've talked a little bit about nil slices and empty slices. Now I want to talk about length versus capacity and what the slice operator does, because the slice operator does one thing that's not completely intuitive. All right, and in the middle of this, you're going to have one of those WTF moments. Right, so I'm going to start with this simple program. I created an array of 3 items. It's called A, and B is going to be a slice of the first item. I wrote it 0, 1. I could have also just written it :1. Either one works. And when I do that and print, right, so A has 1, 2, 3, and B is a slice that just references the 1. Great, we're fine so far. Watch this. I'm going to slice B, okay, which is perfectly okay, right? But I'm going to slice B from 0 to 2. And this is the moment you should start saying, I'm not going to spell that out for you. How can I do that? B was sliced from A with a length of 1, and now I'm slicing it with a length of 2 to make C. Okay, and my first response to this is, this should have a problem. This should just die. And it doesn't. So let's ask ourselves, what's in C? C has the values 1 and 2. All right? Okay. Why that happens is what I'm now going to explain. Because when you do slices, they have both length and capacity. So I want to ask the question, all right, what's the length of B? What's the capacity of B? And when I do that, it has a length of 1. That's fine, because I sliced the first element. But it has a capacity of 3. Now let's do the same thing for C. Let's ask the length and capacity of C. Typo. All right, so the length and capacity of B, 1 and 3, and of C, 2 and 3, all right, and that shouldn't be, the length is not terribly surprising because I did say C is a slice of 2 things. I'm not sure why I should be able to do that, but I notice that both B and C have capacity of 3. Why is that? Well, because the underlying array, A, had 3 items, and so it has capacity for 3 things. And when you use the 2-index slice operator, okay, which implies there's another kind of slice operator, and I'm going to show it to you in a minute. Okay, this is the 2-index, right? I have 0 and 1, or I can leave the 0 out, right? It means the same thing. There's an implied 0 there if I leave it out, okay? And what I've said is start at index 0, go up to index 1, and slice that, all right? That's 1 item. The other one is 2 items. But in both cases, B and C pick up the underlying capacity of A. And so they have capacity greater than their length when I slice them. And apparently Go allows me to slice C out of B with a length greater than B actually had. Because what I'm really doing is I'm going back to the original array and slicing 2 items of the original array's capacity. Now, if I shorten A to 1 item, this should die. Well, no, it didn't die. You know why? Because I didn't do that. Okay, I'm going to shorten A to be an array of 1. That should die, and the answer, it does. Okay, I get down here to C, and I try to slice 2 elements out of B, which really means I'm trying to slice 2 elements out of A, but A no longer has that many elements. All right. But still, I find this counterintuitive. And I really think this is just an original bug in Go. I think that when you slice a slice this way, the capacity should have been limited to the length. It would make a lot more sense. But anyway, let's go back up here because I want to bring in one more. I want to show you a new operator. It was added early on in Go 1.2 in response to a complaint about this very behavior. And it has 2 colons. It's a slicing operator that has 2 colons instead of 1. It has 3 values, all right? And not surprisingly, it controls both the length and capacity of the slice D. And what this says is D will have the length of 1 and it will have the capacity of 1. Now the way that works is if we think of this slice, let me write a comment. If we think of this slice as having values I, j, and k, right, then the length is j minus I and the capacity is k minus I. All right. And now let's go look at what that looks like. So I'm going to copy all of this. I'm going to put it down here. And actually, you know what, just to save so we don't get confused about what's going on, I'm going to get rid of all that for a second. Print lines that are going to confuse us. And just ask now, what is D and what is its length and capacity? Yeah, that one. Okay. So D is slicing C, but I could have done any of these, right? D could slice A, and that would be the result. Well, right? If I slice A the same way, it doesn't really matter. So it doesn't really matter whether D slices A, B, or C. What I'm saying is I'm going to get one element from the underlying array, which is A, and the slice will have capacity for only one element, which means there's nothing extra afterwards. And so if I do this, and then I come along and try to do E is sliced as D, 0 to 2, right? We expect that to fail, right? There's now no magic capacity, and it does. I get there, I try to slice 2 elements out of D. D now only has capacity 1, and so I panic. And to me, the 3-index slicing operator is kind of what I expect by default. When I slice into an existing array and I say I want 5 elements, I think it should give me a slice with 5 elements and just the 5 elements and nothing extra. And the reason for that, I'm going to show you some more examples here in a second of what happens when I try to append to one of these slices. But that's not how it is. So how it really is, if you use a 2-index slice operator, 1:, right, your capacity of the slice is equal to the capacity of the underlying array. And if you don't want that, you have to use the 3-index version. Okay, so let's move on for a second. I want to go back. We're going to recreate A, B, and C. And I don't need D and E right now. We'll just get rid of those. I'm going to want a fancy printf, and so I'm going to create it once so I can copy it a bunch of times. Because what I want to do is I want to show where the slice lives as part of showing the slice. I think I can't do that. I have to have, because A is not a slice, A is an array, okay, it's going to complain about B and C. So let's go ahead and print B and C real quick. But the difference is, for B and C, I can do this. All right. And the reason this is different is because B and C are slices, and I can use the %p on a slice, and I don't think I can use it on an array. So in order to show the address of the array, I'm going to have to actually calculate its address as one variable, as one value, and have the other one filling in the %v. So if I do that, not surprisingly, look at these addresses. They're all the same address. So A, I took the address of the first element. B, I also took the address of the first element that B refers to, which is the same first element of A. And the same thing with C. So A is an array, B and C are 2 slices. They refer to part of A. Okay, we're good. But what I actually want to do now is come down here and start doing some appends. So I'm going to append to C, and then I'm going to print A and C. And let's just start with that one. Okay, so A had 1, 2, 3, B had 1. I went and did an append on C. And maybe I should have printed C before. Let's leave that in there for a second. Okay, and run it. Okay, so I have the first 3 of these, and the first 3 of these just show the values of A, B, and C before the append. And then I do an append to C. And I look at my values for A and C, and they're the same. Okay, well, C was a slice of A's first 2 elements. It had the 1 and the 2, but it has capacity 3, which means there's one more spot in C to put something. But that spot is part of A. And so when I append to C, what I'm actually doing is I'm mutating the A that's underneath it. I'm overwriting A's third value when I append to C. And this is, again, this is part of what I think is unintuitive. If I had defined C this way, we would get a different result. Okay? Because now I'm saying C is a slice of length 2, capacity 2. It represents the first two elements of A, and it's got no extra space to put anything. And if I do that, look at A and C. Okay? A has still 1, 2, 3. C has 1, 2, 5. And it's somewhere else. It's in a different location. So now what happens is, by limiting how much capacity C had, if I append to it, I force a reallocation. There's not enough space in the C that I've just created here with the 3-index slicing operator to put another element, so the append forces a new piece of memory to be allocated. We copy what was in A into it, and then we put this new element at the end in a different location. So A is not changed, and C now has the values of 1, 2, 5. Right? And I'm going to do one more thing just to point this out. I think this is overkill, but I'm going to do it. And again, what I want to do now is I'm going to go modify C0 is equal to some value like 9 and run it. And I'm going to get one more output here. And again, when I look at the bottom of this, A is 1, 2, 3, C is 9, 2, 5. So again, I've got a different place in memory. Once I've limited C up here with the 3-index operator, anything I do to C is happening somewhere else. Now, I shouldn't say it that way. Okay, if I reverse the order of these, I didn't mean what I said, because if I reverse the order of these, the first one of these will still change A. Okay? At the point here where I do assign to C sub 0, C still points at the first two elements of A. All right, so C0 is the same as A0, and it gets changed. All right, and then when I do the append, I get the reallocation and the address changes, and I get the append on the new copy of C with 9, 2. So the order does matter. I made a mistake in what I was saying, right? So if I append first, I get new memory, and then when I assign to C sub 0, I'm not changing A. If I assign to C sub 0 first, it still points at A, and then I do the append, and then I get the copy, and the effect is different. Okay? So, to my mind, you've got two things already going on. You've got slices are aliases to some underlying array. It may have the name A, it may not. If I had created B, all right, let's just get rid of A for a second. What if B, that's going to require me to change all these things here. All right, what if I did something else with B? What if I did B is equal to a slice of int with 1, 2, 3, okay? Now, the difference is just in the naming, because there's still some underlying array, run it, okay? There's still an underlying array with the values 1, 2, 3. The difference is when I made them here on line 8 using this notation, the underlying array doesn't have a name of its own, right? The first case, I created an array A, and then I created a slice B, which aliases A. In this case, I've just created a slice B, and because the B has values, there's some underlying nameless array in memory that B points at. And B is right now on line 8, B is the only name for that space. And then I slice C out of B, and now B and C point to the same space, and they keep doing that right up until I do the append. And when I do the append, C has to get its own storage, and so at that point it gets its own copy of that underlying space and then puts a value 5 in it. Okay? And that's what's going on here. And we see again the same address all the way down here until the very last one. They're all at the same location, this spot in the heap where B was created. Okay, so I talked a little bit about slices. I talked about empty versus nil, and then I talked about slice length and capacity. And I hope I didn't beat it to death, but I do want to bring out a better understanding of what a slice is and how a slice behaves. And I wanted to point out this one corner case of a little bit of unintuitive behavior when you slice some existing slicer array with only the 2-index slice operator. And I wanted to explain why there's a 3-index slice operator and why you might want to use it.